Nice music. I'm not sure it fits the only video I have today to talk about the things that we're talking about. We're talking about forces on structures today. And of course, even though this is moving, the dagger board or the center board of a dinghy or the keel of a yacht, I guess it's a bit different for a keel. Dagger board is just a force against the boat being pushed sideways by the force of the wind on the sail. And once you capsize, because one moment for the sail is bigger than the moment supplied by the dagger board, then you capsize. And if you want to get yourself righted again, then you get on the hull of the boat and you lever the dagger boat to get it up. And so I guess, what is this? Is this a laser? I didn't see the thing on the... Yeah, it's a laser. So the kind of concepts that we've been talking about. So you know what the force would be on the sail. It would be kind of a set force of the wind having its velocity broken and v squared over 2g being turned into p over unit weight. We'll talk about Bernoulli beginning in week 4, next week, I guess, a week today. But the forces acting on the dagger board, even though it's moving, we could ignore that, would be this prismatic distribution, triangular distribution, getting larger with depth. And so the net force that's acting, we could calculate, because we know how to calculate F sub r. And we also know where that force acts, because we have Y sub r, its location of action. And so we could do a moment diagram to be able to see what the net moments are as to whether it capsized or not. So that's what we're attempting to do. So maybe let's get going. I can end that. So that's where we're our plan for today. So we've talked a little bit about this. Is that beer? Yeah, good. Good response. If it's beer, then you should share it. All right, so I digress. So fluid statics and pressures. Actually, I will make the point that I saved you a lot of math last time by doing the things that we talked about. And it was a relatively simple presentation that kind of explained what we're doing, came up with this diagram that's defined the two things that we need to know. One is the force of the resultant that acts on a plane, which is a function of a number of different parameters, and its location of action. And so those are the two things that we need to know. But once we have those, then we'll do some examples that take that information and look at failure modes of different structures to be able to do something useful in an engineering sense. And so that's our goal today. So I just want to recast what we talked about so far. And I was going to illustrate it with this simple point here, that if we would take a bar, and on that bar at half height, we could have a force which I'll call F square. And if we could have another force acting on that bar, which I'll put at 2 over 3 h, and this is half h, then, and this is what I'll call F triangle, then we can get the resultant force, which is equal to the sum of those two, right? Just by resolving horizontally, sum of forces in x is equal to 0. So the resultant that we have acting against it here, bless you. So just a bar that these are acting on, so statics, this would be F square plus F triangle. And we know that these have to equal the force acting in the other direction because it's in equilibrium. And so we could use that to be able to say something about this system, because what we don't know is we don't know what this lever arm is, which we'll call y sub r. And so what we could do is we could take moments about here, and so if we take moments, what do we get? We get, going in the counterclockwise direction, FR YR equals a half F square plus 2 over 3 F triangle, both multiplied by H, right? Just multiplying these. So that's a simple statics problem, just for a bar that's dangling down, half height, 2/3 height, resultant acting in the opposite direction. But that's exactly what we are doing in this, and we could calculate, so we know what this is, because this is equal to just the sum of F prism plus F triangle, because of this. And so the only thing that we are left to calculate is the resultant, which we can get from this. And so now if I take away the mystery, I'm not taking away the mystery, and I draw some pressure prisms. So this is the force that is acting due to this. Force that's acting here is really a distributed stress on a plate. And this is the triangular distribution. Then I'm just trying to be very clever here. If I do this, so this is exactly our distribution that we have here. So this would be the distribution on the plate due to the pressure that's acting at this point here. So what this would be, if this was Z, then this pressure at any point would be equal to unit weight of water times Z. At this point, Z is 0. Forget the fact that we've ignored our sign convention. And then as we go further down, then it would be equal to a larger number. And so this is really what we're doing in the sub-C, the sub-lake, is we're taking a pressure distribution that's uniform, that we've just divided. The real pressure distribution on this due to the fluid would be this distribution here, because we know the pressure at this point is this. So if we wanted to, we could define this as P. So in other words, this would be P1. This would be P2. And then P is equal to P0 plus gamma Z, right? This would be P0, 0 depth. And so the distribution that we'd have on this would be what I'm going to color in here. And so if you think about doing it discretely, for a bar that has a force here, and together the sum of those two forces has to equal the resultant, you can take moments about the top of the bar, or you can take moments 10 feet above the top of the bar. You still get the same result. You can calculate the location of action of this force, and it would be true. It would be correct. And so what we did last time was we did basically, well, we didn't do the last part. So what we could do now is we could do this to be able to represent our system. And so the other way that we can look at this would be to to do this. Again, to have this. And the distribution of pressures on this would be this. This would be the top here. Let me just draw a straight line because I'm going to do some different things. And so now the magnitude of the force that is acting here, we could calculate from this. And we know that our way of doing this is to take the pressure at half height. It's not quite half height. Where this is h sub c. And we take this and we do this. We subtract this and we add it here. And therefore that is why the resultant force is always equal to the unit weight times hc, which is the pressure at this point. P average is equal to unit weight hc, and multiplied by the area of the plate. And of course the area of the plate would be this plate that's standing up. Or I guess I could use my piece of paper as I did last time. And so that is always true. And the location of yr is always equal to this other expression, which this parallel axis theorem here, which is second moment of inertia around the centroid around the x-axis, the area of the plate yc squared plus yc. And so in this particular case, the coordinate direction that we're doing is this. And so yc is this value. It's along the direction of this axis. It's this. If it was tilted, y would be inclined. And so we can calculate the point of action. So the magnitude is given by this, but importantly, its location of action is given by this. Magnitude is there, location, and this is what we'll call delta c, delta y, and this whole thing we'll call y uppercase R. Okay? So now I want to take the same plate and I want to rotate it. And so if I rotate it and I do exactly the same as I did before, then the pressure acting at this point will be equal to whatever this depth is. The pressure acting at the bottom will be whatever this depth is. And again, it's joined by those two. If I take this and I divide this into this by subtracting this and adding this, then again you get the fact that the average pressure, which is here, is at the depth of the centroid. So this is the average pressure, P bar. And of course this term here is the average pressure. Depth of the centroid and unit weight, product of the two. But now, I guess importantly, the y-axis, which I'll draw in green, does this. So this is y, and so now This is YC. This is delta Y. And this total thing is Y sub R. And true to form, the location where the force acts will be through here. FR. It's the same magnitude as this because HC is the same. But the location where it acts is at the same location on this plate. Actually, no, actually it's not. Forget that. Delta Y here is not the same as delta Y here. It's changed. So the magnitude will be the same, but the point of action will change. And so the final proof of the pudding, if you like, would be a plate which again is at the same height, but is horizontal. So now the pressure distribution on this plate, if I do it in blue, is going to be this and this. We don't need to subtract anything off. This is P average. P average is equal to unit weight times HC. This is going to be HC. And I suppose the challenge would be to think what YR is. YR is this. So you could think about this being Y. This goes to infinity because it's horizontal. And so if it goes to infinity, so then YC, in this case, goes to infinity. And if you calculate this here, that means that Y sub R is equal to Y sub C. And so Y sub C is just the location of the centroid. And so in this particular case, the force acting on this plate has to act directly through this point here. The force for all of these resultants are exactly the same because HC is the same. The locations where they act are different on the plate because it's being turned. I guess in this particular case, FR will be the lowest, below the centroid. And in this case, FR will act right at the centroid on the right-hand figure. Right? So that's what we're doing. Yeah.
Sorry, quick question. So is this still based off of the, so this is based on the centroid problem that we were working on Monday?
Yes.
What exactly would be the difference between YR and HC in this case?
YR is the slope distance. Y is the slope distance to the plane. HC is the vertical distance to the plane, always. So if the plane's vertical, then the YR and H are coincident. If it's flat, then they're orthogonal and they're not related. Well, yeah. Slope distance versus vertical distance. And if you always remember that, you always get the right solution. Okay. And so I don't really. This is a summary of what we did last time. You remember that what we did was we want to calculate. I don't know if it's worthwhile doing this. We calculated the resultant force, and what we did was we said the pressure at a particular point is equal to the depth of that point below the surface, and we're multiplying it by the area of a stripe along on this. So a differential stripe across this is what we're representing. And so if we realize that the width of this stripe is some width W multiplied by dy, so that's the area of this stripe, the pressure is equal to the unit weight times how deep we are, y the depth. We do the integration, we end up with our expression, and this expression is just equal to gamma h sub c a. This is what this integral is. If we take a moment about this, as we did just now in this purported beam, nothing scary, right? We take a thing, force acting here, force acting here, force acting here. We can take moments around this to be able to resolve what the height, the depth, YR is on the left-hand side. That's all we did in this particular calculation. We can also write the moment for this distribution by taking the pressure that acts here and multiplying it by the lever arm, which is y, which is this term here. And if we go through this, we get something. So then if we take the moments about any place, we could choose the top and equate it against the resultant force times its location of action. If we know what these moments are and we know what this force is, we can calculate the point of action. And if we do that, then we get this. Don't need to know how to do it, but you need to know kind of where it comes from. That's the rationale by which it works. And of course, you can take these moments about structures to do it yourself if you want to, but we can also use these standard results. And this is the standard result we've looked at. And I guess I wrote it wrongly, perhaps before. Did I put an extra squared in? Incorrectly, and yeah. So no squared here. So that's a standard result. And the standard result for this term here, always given to you in a test if you have it, as you see if you've looked at any of the tests, are just out of Munson. For the geometry we looked at here, this is the centroid. I didn't crease this one. Remember what we did last time? The center of gravity of this piece of paper is just here. And this is the centroid here, the balance point. And this is B, and this is A. And the second moment of area about the centroid is a half B A cubed. And we have it for different shapes. For the centroid of a circle, if I cut this in a circle, it would be in the middle, of course. And the second moment of area is pi r to the 4 over 4, standard result. And I mention that because we will use this right now in a second. Okay? Everyone good? So here's an example. We want to calculate the forces that are acting on a poker chip, which is 10 meters in diameter. So it's not a poker chip. It's sitting vertically below water. We want to calculate what the force is that acting, Fr, and we want to calculate what the magnitude of that force is. Done backwards, I don't know why. What's the point of action? We know that, or we can guess, that if we're below the surface, then the pressure diagram for this converges at the surface, and we're going to have a prismatic distribution and a triangular distribution, and almost certainly the resultant force is going to be below the centroid. As we come up exactly to the surface, it'll still be below the centroid. The only case where it won't be is this case here. So how do we do this? We look to evaluate this here. So IXC is pi r to the 4 over 4. Our standard result. Don't want to give you whiplash, but you saw we had it before. And so we want to calculate what YR is using this. So IXC is this. YC is this. A is this. A is the area of this disk, so the area is equal to pi r squared, uppercase R, I guess. The location of action, YC, vertical disk, water up here, distance in the plane to the centroid, so it's the distance from the surface to down here. It's going to be 5 meters plus 5 meters, it's given here, and so it's this 10 meters. And the second term here is going to be 10 meters as well. Add them together and do the math, you end up with a distance below the surface of 10.62 meters. So this is 10, which is y sub c, and this is delta y, sorry. So we end up with this. YC we know because it's the depth of the centroid. And delta C we've just calculated, which is 0.62. So the total amount is, so this is delta Y. Okay. Standard result. If we want to calculate the force that's acting, then we can use this. Unit weight of water, 9.8 kilonewtons per meter cubed. H sub C is the depth of the centroid vertically. Our y-axis is vertical in this case, it's not canted over, but regardless, H sub C is this distance. And so in this particular case, y sub C is equal to H sub C, which is 10 meters. And so if you use this, multiplied by the area, which is pi r squared. I didn't do the calculation, but if you do the calculation, I think you come up with this. This is in Munson, by the way, so you can see this result. Okay. So we've calculated the two things that we want. We did it ass backwards. We usually calculate force to get the magnitude of the force and then figure out where it acts, but it doesn't matter. We've got those two pieces of information. So it acts at this point here, and it's equal to 7,700 kilonewtons. Okay, so good. So let's use it usefully. So now we're going to take this disc, we're going to put a hinge through it so it can rotate about this hinge, and we're going to put a wall above it and a wall below it and a wall on the other side, and it's circular. And so this is exactly what it looks like. So this is a side view. The hinge would go through here, which it can rotate around, which is this point here. And we're going to have water on one side and water on the other side, in which case the force acting on one side is going to be equal to the other side. If you look at the distribution of the pressures, they'll look like this. I'm going to remove that in a second. Highest pressure here, lowest pressure here, highest pressure here, and this amount here is 0.62. This is what we've called delta Y. And so, fine. Has to be acting the same in both sides. Let's drain the other side, and let's put a backstop here. So we know that when this force goes away, because we've drained this side to this, then we know that this gate will tend to be pushed by this force. There's nothing acting on the other side, so it'll tend to rotate like this. And so if there's no backstop here, it will just fail and all the water will escape. But if we put a backstop here, we want to calculate what's the design force that we have to apply for this backstop. And so we got this location by using moments. We could take moments around anywhere to get that, because that's where this equation comes from, by taking moments. But now, if we want to talk about a failure mode here, we want to take moments about that failure mechanism. So the moments have to be taken about the hinge. So we can just take moments around this. And so what will that equation be? We can look at the moments going counterclockwise. So the counterclockwise moments is this force to shut it multiplied by this lever length. L shut, I guess. So F shut times 5 meters, because this is the radius of this. We don't know what this is, but we do know what the other moment going in the counterclockwise direction is, and it's equal to this force multiplied by this lever arm, which is our delta Y. And delta Y is this. So we know the force, we know the lever arm, and so the only thing we've got to calculate is the force that's shutting it. Right? And that's that. And that's why we do this, just to be able to do those calculations. So if you have a gate which you wanted to work like that, you'd have to apply some kind of rivet or backstop welded to it that provided enough force, strong enough to be able to resist this, right? Good. Throw me a bone here. Too slow, too fast. Okay, so it's all in your notes. So we can use those standard results. Another example. That's the only other example I wanted to do today. We get these standard results. Yeah, we don't need this. Okay. Everyone okay with the previous one? Silence means yes, I guess. Or no response means yes. Okay. Another one. So perhaps a little more complicated. Same idea though. You've got water behind some kind of structure. The structure has a hinge here, is able to rotate with the force of the water, pushing it towards your right in this direction. And to stop that, you need to apply a force. So what we need to do is define a free body. And that free body is here, but it's predicated on this kind of figure that we would have, which is a gate here. So what is it? It's hinged at O, so it can rotate around this point here. What is the minimum horizontal force P that we need to hold the gate in place? It's 3 meters in width. And so how do we calculate the magnitudes of the forces that are acting, force 1 and force 2? So we look at the gate. We calculate the centroid of the gate. We know our expressions are equal to, the resultant force is equal to the unit weight of fluid, the depth of the centroid multiplied by the area. And so for this, what will those be? It'll be the unit weight of water in this particular case. What's H sub C? Three meters plus 2 meters to the half height. So that is and what's the area? That's equal to okay, 3 meters wide, 4 meters tall. That's the area of the gate. So that's the area. And so this is the resultant force. So this, in this particular case, is equal to F1. The more challenging part, and so you see this calculations here, this is 3 plus 2, this is 4 times 3, etc. All worked out good. The location of action, YR, is equal to I, the second moment of area of the centroid around the x-axis. Isn't that horrible terminology? Area times the centroid location plus YC. Let me check whether that's right. Yeah, I guess so, because I'm not so smart. And so what are the standard results? You remember that IXC for a plate is equal to BA cubed over 12. B is the width, A is the, doesn't matter if it's the profile of the plate. The plate could be horizontal, but it's the profile of the plate. This has to be with the depth. And this just comes from this. And we've used it before. And so if we do that here, this is BA cubed over 12, that's this, times the area times YC plus YC. And so let's see what these are. What's YC? Well, YC is in the plane of the thing. So if it's like this, it would be like this, but it's vertical. So YC is just up to the surface, and so this is equal to also YC. So this is equal to 3 plus 2. Meters, of course. Area, we've calculated the area before. It's equal to 3 multiplied by 4. So we know what this is. We know what this is. And IXC is going to be B, which is 3 meters. And A cubed will be 4 cubed. I think this is down here. You can look there. So don't need to, you just need to know what those are. It's a recipe, right, to be able to calculate what they are. So we know the second moment of area about the centroid around the x-axis, which is B A cubed over 12. And so we can calculate what that location would be, and that would give us this depth to the centroid, and this would be what we've called delta y. And that means that this total height here would be y sub r. Sorry if it's getting crowded, but that's it. So we know the magnitude of the force that's acting horizontally, which is F1 here, which is this. And we know the location of action for it, which is YR1, which is this. So this is YR. I guess we could call it YR1 because we're calling this force 1. And this is F. If we wanted to, we could call this FR1. Or perhaps not, because they don't in the text. F1. Let's just keep F1. So that's the hard part. So now we need to know what the force is that's acting. Everyone's okay with that, right? So now we need to know what the force is that's acting on this base. Easy one, because we know it's exactly going to look like this. We know that H sub C is going to this. We know that Y sub C is going to be infinity. And so it's going to act at the center of pressure of this base. So it's here. The centroid is in the crisscross. So it's going to act physically at that crosshairs. X crosshairs. It's not a crosshairs in a scope. And so the force, again, is going to be the average pressure that's acting. P bar is the unit weight times the depth below the surface. H sub C is going to be 3 meters plus 4 meters. So it's going to be 7 meters, which is what this is. The area of this plate is going to be 2 meters by 3 meters into the page, which is this here. And the unit weight of the fluid is this. So these first two terms are the average pressure, P bar, and this is going to be the area in which it acts. And so we multiply those out, and we end up with this. So we know now what the force acting vertically is. We know what the force acting horizontally is. We know the location of that force because it's some distance below the surface, which is YR1. Remember, it's not from the top of this hinge, but it's up to the surface. And we know the location of action of this. It's just in the middle. I could have drawn this, but you know that this plate at the bottom, if I draw it in perspective, is going to look like this. X gives this. So the force 2 is acting here, right in the middle. And so now we have the magnitude of this, and we also have the location of this, which is, if this is 2 meters, Then this is 1 meter, which is, we'd call L2, I guess, perhaps. Not sure. And we know the location of action of this. What was y sub r? This is 5.267. So 3 of those meters are to the hinge. So 2.267 is to the point of action. So this is 2.267 meters. And then there's 3 meters up here to the surface. So that together these are 5.267. And then we know where this acts. We know this magnitude, we know this magnitude, we know where this acts, and we know where this acts, and we don't know what this is, but we know where it acts. And so this lever arm is just equal to the depth of the gate, which is 4 meters. And so now, if we take moments, and importantly, only 3:37. Importantly, unlike what we've done before, when we could take a moment about any place and we could resolve to get the locations of the forces, now we're looking at a failure mode. So we have to take moments about the hinge. And so we take moments about here. And so if we go down to the base, this expression here should be exactly that. Taking moments about the hinge, the force 1 multiplied by L1. So L1 is 5.267 meters from below the surface, but the hinge is 3 meters below the surface. So that's what this length is. So this is force 1, and this is the lever arm L1. This is force 2, which is acting the same counterclockwise direction, because this is pulling down. And so if you looked at that force here relative to here, it's twisting it. So this is added. It's equal to force 2, which is this term here, multiplied by the lever arm, which is 1 meter. This is what we don't know. And this is the countering lever arm that's pushing it in the other direction. And this is just equal to 4 meters. And from that, we know both these values here and here. We don't know the value of P, but we can calculate it, and it's equal to 436 kilonewtons, a force that we've calculated. Okay. So that's the rationale. So just to ad nauseum, I don't want to be a pedant, be pedantic about this, but to make the case that we calculate the size of the force by using this general expression. Importantly, h sub c is the vertical distance to the centroid below the surface, always. And this is always true. And it doesn't matter whether we are vertical, angled, or horizontal, always true. And the reason is because of these plus and minus pieces. All we're doing is, if the plate is centered at the same physical depth but it's rotating, the average pressure acting on the plate is always going to be the same. P times h sub c, unit weight times h sub c. And whether it's rotated or not doesn't matter. The average is all the same. And rotating it, all it does is it allows us to subtract and add these little triangular regions that cancel out. So that's always the same. And the other thing is that we use the location to that center of pressure. And that is done by drawing a coordinate axis which is in the plane of the plate and intersects the surface, just like we drew here. Oops, trying to draw on something that's not there. So this y sub c is always the distance to the centroid from the surface. This is the kind of perspective view of that. And the location of action will always be some amount delta y below that. And this total length is what we'll call what we do call y sub r. Always true. Gets a bit complicated if it's horizontal, but it's also easy when it's horizontal, because you know that when it's horizontal, the pressure is going to be uniform everywhere on the plate. And so in this particular case, the centroid of the plate is actually the center of pressure where the resultant acts. Okay. In all other cases, the center of pressure will always be below the centroid by some amount, delta y, always below. And I guess it will be maximally below when the plate is vertical, and progressively it'll creep up towards the center of the centroid for when it's horizontal, kind of shown here. So, and I guess my introduction to I didn't want to be a pedant was to make the case that we get this parallax theorem by taking moments about any point to be able to resolve what y sub r is. But if you're looking at a problem where you have a structure which is failing in some way, it's rotating around a hinge, then you have to calculate the force and its location of action, and then take moments for that failure mode, if you like, around here. And we did it for this disk, which is like a gate, which has a backstop to it, and this contrived geometry where you have to apply a force here to be able to stop all the water rushing out from this. Okay. Wow. So you need to realize these standard results. If you look at the past tests, you're given these in the question, if that's the question. They're different from different shapes. We dealt with a circular disk. We dealt with a rectangular prism. You can also do it for a semicircular or a triangular prism or a quadrant. The C is the location of the center of the centroid. And so if you had a quadrant and you put it on your finger, this would be the point that it would balance against. And the idea is that you integrate over this whole surface. You probably don't really care. You integrate all the little differential areas, d, r, d theta, multiply it by its little piece of weight, and you look at the lever arm, which is this length here, and when you sum those up on the whole disk, the one point where those all sum to zero is the point that it's supported by. A bit like looking for the center of the U.S. I think the center of the U.S. is something like Pierre, South Dakota. It's if you took the conterminous U.S., excluding Alaska and Hawaii, and hold it on your finger, it would balance around South Dakota. So same kind of idea. Pierre, not Pierre, I guess, even though it's spelled that way. All right, everyone okay with that? What else? Everyone okay? Great. Yes.
Yeah.
Well, no, I wasn't prompted in a response. I took it as a yes. So what else? We usually work in pressures, gauge pressures. So we usually take the pressure here as being P equals 0. P0 equals 0 pascals gauge. But we could also use P0 equals 10 to the 5 pascals absolute. Doesn't matter. It cancelled out. And the reason it would cancel out would be that there'd be just there'd be 10 to the 5 pascals here. And there'd be 10 to the 5 pascals added on just as the same prism on the other side, right here. So this would be 10 to the 5 pascals. So it's easier to work in gauge just because we ignore absolute pressures. And this is the little diagram that we drew before. So now you understand why I used triangle and prism, is that if you have a plane below the surface, you can always decompose the pressure at the top and the pressure at the bottom. If this is in this orientation, not tilted, if this is parallel to the free surface, the pressure at this point, this point, this point, and this point are always going to be the same, and different from the magnitudes at this one, but they'll always be the same magnitude, so you can always describe this pressure on the leading edge, this pressure on the lower edge. It absolutely has to be a linear distribution between these 2 points because you're going down incrementally, linearly in depth HC, H, I guess. And so this distribution here is also linear, and so you can always decompose it into a triangular distribution and a prismatic distribution. If you do that, you know that the prismatic distribution will always act through the centroid. The triangular distribution will always act below the centroid by some amount, y sub c. And actually you know that this distance here is going to be equal to what? If this is h. No, if this is L, what is this distance here? Standard result. You can get it also from using our parallel axis theorem, our y sub r, but the location of the triangular distribution is always going to be acting 2/3 of the way down this distribution, 1/3 up from the base. And the distribution for this prismatic distribution will always be the centroid. Delta y is equal to 0, and I guess delta y is equal to 1/6, right? This would be 4/6, this would be 3/6, and this would be 4/6. So, and I guess this is the point I was making before. I forgot it was at the bottom. We can use gauge or absolute pressures. We just have to add them to both sides, and they cancel out. So why bother unless you need to?